Okay, in this video, I want to give an example problem involving uniform convergence. So suppose that we have the sequence of functions fn that's defined by f sub n of x is 1 over 1 plus x minus n squared. And we're given that the sequence f1, f2, f3, dot, 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 converges to the function f, which is defined by f of x equals 0. So f is just the constant function 0, and we don't need to prove that the sequence converges, although we should know how to prove it. In this problem, the question is just asking whether the convergence is uniform. So, uniform convergence, okay, it really helps to know, to decide if the sequence converges uniformly, it really helps to know what the limit function actually is. In this case, we're told that it's just f of x equals 0. So intuitively, what's going on is, okay, first, we're not given whether the convergence is uniform or not. We have to decide, and we have to prove it. But before proving it, either one or the other, we want to get an idea of which one it's going to be. Is it uniform convergence or not? And our limit function, f, is just the function given by f of x equals 0. And remember what uniform convergence means. It means that for every epsilon, there is a capital N such that for all little n greater than capital N, the f sub n's are always within epsilon of f. So in this case, what we need is for every epsilon, we need some integer capital N such that for all little n greater than capital N, the f sub n's are always within negative epsilon to epsilon, within this band. And if you imagine, so now we have to ask, okay, does that happen? And now we have to look at the individual f sub n's. It's 1 over 1 plus x minus n squared. Well, what's going on is, okay, let's look at the graph of g of x equals 1 over 1 plus x squared. So what's going on is when you plug in x equals 0, you get 1. And then this function has horizontal asymptotes of 0. Right? It's like this. That's what the graph of this function looks like. And notice that your f sub n's is just g of x shifted to the right by n. So your f sub 1 is going to look like this. Your f sub 2 is going to look like that. Your f sub 3 is going to look like that, and so on. Now, do you think, just from this, is there going to be a capital N such that for all little n greater than n, and for all p and r, f sub n is between negative epsilon and epsilon? Well, no, right? Because what's going on is that these peaks, there's always going to be an x for which, no matter what your n is, there's always going to be an x for which your function takes the value 1. That's what's going on. And so we should expect the convergence to, should we expect it to be uniform? No, right? We expect that the convergence is not uniform. So we will prove that the convergence is not uniform. And often for proving that a sequence doesn't converge uniformly, it helps to use a proof by contradiction. You don't have to, you can always arrange it so that it's a direct proof, but psychologically it's just easier if you try to prove it by contradiction. Okay. So we need to pick an epsilon. So suppose not, right? Then we know So suppose that the convergence is uniform, in other words. Suppose the convergence is uniform. And we're going to deduce a contradiction. Then we know that given epsilon greater than 0, there's some property. Now, what epsilon should we take to get a contradiction? We should take epsilon to be less than 1, right? Anything less than 1 because, well, we probably could take epsilon to be equal to 1. But we should take epsilon to be less than 1 because we know that, if you take epsilon less than 1, then you're going to be able to find x. No matter what your n is, you're going to be able to find an x for which f sub n of x is greater than 1/2. Right? So suppose that the convergence is uniform, and then let epsilon be 1/2. Then by the uniform convergence, so for every epsilon there is an n, such that for all little n greater than capital N, the f sub n, I'm just going to write it out, f sub n of p, so for all p in R, the distance between fn of p and f of p is less than epsilon. Actually, since I'm working with I usually reserve p for elements of arbitrary metric space. Maybe we'll just use x. Okay, whichever letter you want is fine. Right, and now we have this inequality that is supposed to be true, and then what we're going to do is we're going to find an x for which the inequality is not true. Right? And then that will be the contradiction. Well, so what does this inequality tell us? This f sub n of x is 1 over 1 plus x minus n squared, and then minus 0. So this is less than 1/2. But now what we want to show is given n, given little n, there exists an x for which this is not true. But for any n, okay, what's an x depending on n for which this inequality is not true? N, right? So if you plug in x equals n, you just get 1 over 1 plus 0 squared, and you get 1, and that's certainly not less than 1/2. So, but for any n, okay, if x is n, 1 over 1 plus x minus n squared, absolute value is equal to 1, which is greater than 1/2. So that's a contradiction. A contradiction to the inequality that we just found. And so therefore, the convergence is not uniform. So that's a typical way of proving that a sequence doesn't converge uniformly. What you do is you prove, so first of all, you get an idea of what the fn's look like. That's really important, because otherwise you're not going to be able to tell, right? You kind of have to know what the graph of these functions look like in order to do this problem. The 1 over 1 plus x squared, and then recognize that the graph is that just shifted to the right for each n. And then it helps to know f and then draw the epsilon band and then ask, okay, are these functions eventually all lying in this epsilon band? And once you look at the graph, it's clear that the answer is no. So then you say, okay, the convergence is not uniform. And then when you do this analysis with with these functions, your fn graphs and then your epsilon band, you ask yourself, okay, what's the issue? And the issue is the fact that these GNs, these FNs, all reach the point 1 at some point. And so that leads you to the epsilon. You take epsilon to be less than 1 in this example. So in this case, we just took 1/2. And the idea is to use a proof by contradiction. That just makes it easier because you get this inequality to work with, which you can contradict, right? You can look for an x for which the inequality is not true. So we suppose the convergence is uniform, and then you take epsilon to be 1/2. Then by the uniform convergence, there's a capital N such that for all little n greater than n, the distance between fn of x minus f of x is less than epsilon. You write out what that inequality is, and then you find an x. Okay, for all n, for any little n, you find an x, so possibly depending on n, for which this inequality is not true. In this case, we took x equal to n. And then that's a contradiction, and therefore the convergence is not uniform. That's often how these proofs of non-uniform convergence go. This is a very typical example. Okay, thanks.